Hello all. So today we'll try something a little bit different from what we have been doing all this time, and we will specifically go over paper 2, which is called Advanced Physics 2. So we will go over paper 2 from the Edexcel exams, and I believe that this will be useful from any potential students from the UK, because I think this is what people takes in the UK. So it is called Pearson Edexcel Level 3 GCE, and this is a test from June 2024. I don't know if it's called May 2024, but I guess that's the exam period. Okay, because most of the students that watch these videos take the international, the Pearson Edexcel International A-level physics, I will be pointing out that, okay, this problem is also suitable for unit 2, 3, 4, 5, whatever. Okay, so with this being said, I guess let's just start and see how this goes. Okay. Question 1. This is a multiple choice. This is the multiple choice section. In the international exam, this is called section A, but this is not the case in the UK exam, I guess. So, question 1. A Hertzsprung Russell diagram for stars in our galaxy is shown. V, W, X, Y, and Z are positions on the diagram. Which of the following gives a sequence of positions of the sun during its lifetime? Okay, so first of all, you need to observe that this is the sun at position X, right? Because the luminosity of this cluster of stars is 1, just like the sun, and the surface temperature is about 6,000 Kelvin, which is about the surface temperature of the sun. Okay, what's going to happen to the sun? It's going to turn into a red giant, and then it's going to turn into a white dwarf. What's the correct answer? B, right? Yes. So let's move on to question B. And for students from the UK who might be watching this video for the first time, I try to explain what I'm doing as much as possible, and I mean, this is my style, so let me know in the comments how you like this video. So and this question can also be, I mean, question 1 can also appear in unit 5, okay, from the international exam. Okay, question 2. A satellite of mass m orbits the Earth with speed v. Okay, what is the speed of a satellite of mass 2m at the same distance from the Earth? And the answer is kind of simple. It's b, right? It's the same. Why? Because the centripetal force is provided by the gravitational acceleration. The gravitational attraction, Newton's law, which is given by g times the mass of the Earth times the mass of the object over r squared, and this should be equal to the kinetic energy of the object, which is 1/2 mv squared. And m cancels, right? So this speed does not depend on wait, what did I write? I'm sorry, I made a mistake. We're talking about forces, and I set the force equal to kinetic energy. I'm sorry, guys, okay? Mistakes happen. So this is equal to mv squared over r, okay? So the mass of the object still cancels, and so does this one of the powers of r, and the velocity is actually the square root of g times m over r. And you see it doesn't depend on the mass of the object, so it's b, okay? So actually, I'm going to be commenting that this question is not relevant to people taking the international exam when a question is totally different, okay? Because that's going to be easier. Okay, question 3. The isotope francium 221 is the mass number, and 87 is the atomic number, the proton number, okay? Undergoes a series of alpha and beta decays before forming thallium 205. Okay, which row of the table shows the number of alpha and beta particles emitted during decays. Okay, so for this one, maybe I will use a clean page. So we have FR 22187, and it undergoes several decays before turning into TL 20581. Okay, so first of all, let's subtract the mass numbers. So 221 minus 205 yields 16. And now let's subtract the proton numbers. So 87 minus 81 is gives you 6, right? Okay. First of all, alpha decay decreases mass number by 4. Okay. And alpha particles have 2 protons and 2 neutrons. Therefore, we need 4 alpha decays to match 16 number of protons gone, right? Because we have 16 protons and neutrons gone from when we turn francium into thallium, okay? But then, with 4 alpha particles, we change the proton number by 8, right? So with 4 alpha decays, we change Z by 8, okay? But in our problem, Z changes by 6, okay? Therefore, we need 2 beta decays to change proton numbers to 6, right? From 8 to 6, because beta decay is the only decay that can change the number of the atomic number, okay? Alpha decay cannot do that. Beta decay cannot change the mass number, okay? And yeah, the answer is then, what is it? C, over here, okay? I hope this makes sense, okay? And let's move on to question 4. In an electron diffraction experiment, electrons are accelerated by a potential difference between a hot filament and an anode. The electron beam produced strikes a sample of crystalline material, causing a diffraction pattern. Which of the following will cause the angle of diffraction to increase? Okay, we have to use 2 equations here. I'm going to use the clean page again, okay? And this question 4, actually, we don't need the number, it's okay. So, n times lambda should be equal to d sine theta, right? So sine theta for diffraction patterns. And by the way, for students who are taking the international exam, this is irrelevant to you. For units 4 and 5, okay? No question like that will ever appear. So sine theta is n times lambda over d, okay? And then we have to also use de Broglie's wave equation that connects the momentum of an electron to its wavelength, and also the kinetic energy of this electron should be equal to E times V, where V is the potential difference, right? So if we combine these two, we get that lambda is h over the square root of 2 times m times E times V, okay? So if V decreases, lambda increases, therefore theta increases, and the correct answer is B, okay? So I hope this makes sense, and I hope this is useful. I can take an extra step and write sine theta equals to n over d times this is n over d times h over the square root of 2em v. And now it's obvious, I guess, that if we decrease v, the potential difference, lambda will increase and theta will increase as well. Okay, This is the first question we encountered that is relevant to students taking the international exam. Okay. Question 5. The particle P has charge and mass. Okay. The particle causes an electric field and gravitational field. Which of the following statements is correct at a distance r from P? The gravitational field strength is the gravitational field strength is proportional to 1 over r. That's wrong, because it's proportional to 1 over r squared. Electric field strength is proportional to 1 over r. Also wrong, because it's proportional to 1 over r squared. C, gravitational potential is always positive. No, it's always negative, right? Because it's attractive, okay? So D is the only one left. Is it correct though? The electric potential is proportional to 1 over r. That's correct. So D, right? Okay, question 6. The graph shows how binding energy per nucleon varies with a nucleon number for atomic nuclei. The arrows W, X, Y, and Z represent changes in binding energy per nucleon and nucleon number. Fission and fusion of nuclei may result in the release of energy. Which row of the table gives the arrows representing energy released by fission and fusion? All right, so this is the part where fission occurs. Okay, so about there is iron 56 iron. Therefore, to the right, fission causes energy release, and to the left, fusion causes energy release. So W and Z. So C is the correct answer. Okay. Okay, I mean, Z represents a heavy nucleus splitting into two lighter nuclei with higher binding energy per nucleon. Therefore, we have energy release. And in the fusion side, we have two light nuclei merging into a heavier one with energy being released due to forming a nucleus with higher binding energy per nucleon. Okay. Question 7. This is another question that will not appear in the international exam, okay? So the diagram shows a ray of light passing from medium X to medium Y to medium Z. The speed of light in medium X is Vx, the speed of light in medium Y is Vy, and the speed of light in medium Z is Vz. So how do we think about this? So if the ray, so ray bends towards normal, means that we have an decrease, so V decreases. If ray bends away from normal, actually everything is squeezed there. I'm gonna use a clean page. It's cleaner. So let's do that. So again, so ray bends towards normal means that V decreases, and if the ray bends away from normal, V increases. Okay, so let's go look at the scheme. So let's start here. We see that the ray of light bends away from the normal, therefore V in the region Z is larger than V in region Y, okay? Yes, and now in this region we see that V, let me think. So we have the ray bending towards the normal compared to what it was in region X. Therefore, Vx is larger than Vy, okay. And now to compare Vx and Vy, we see that in region Z, the ray of light bends more, right? So the speed is the largest in region Z, right? So Vy is the smallest velocity, okay? And then we have Vx and Vz, okay? And again, the justification for that x is smaller than y is because in region Z, the ray of light bends more than in region x. So the answer is A. And again, this is a question that is irrelevant to people taking the international test. So, question 8. A weight of 2 newtons is suspended from a spring of spring constant 50 newtons per meter. What is the elastic strain energy stored by the spring in joules? Okay, first of all, we have to find x, like the extension, okay? How can we find that? So the weight, 2 newtons, should be equal to k, which is 50 times x, right? Let me erase the newtons, I don't need them. So x is 2 over 50, right? And this is in meters, right? Yes. So the elastic energy is 1/2 times the force times the extension squared, which is 2 over 50 squared. Okay, so this 50 gets cancelled with, actually, okay, this looks confusing. Okay, 1/2 50 times that, which is equal to 1/2 50 times 2 squared over 50 squared, and now we can cancel. Okay, so what's the only correct answer? D. All right, moving on to question 9. Okay, a mass is suspended from a spring and displaced vertically. The mass performs simple harmonic motion. The graph shows how the acceleration of the mass varies with time over one oscillation. And the equation describing this is omega squared A sine omega t. How do I know that it's a sine? Because at time 0, the acceleration is 0, and then at time t over 4, we get a maximum, okay? So this looks like a sine function, so that's the acceleration, okay? Which of the following graphs shows how the velocity v of the mass varies with time t over the same interval? Okay, so A and C are obviously wrong, okay? So the only options are B or D. So B and D are cosine functions, right? So they will look like this, omega A cos omega t, okay? But the derivative of cosine with respect to time is minus sine, right? But the acceleration, and that will give you the acceleration, but the acceleration is positive, therefore we need a minus sign, and immediately we see that the correct answer is B. I hope this makes sense. Let's move on to question 10. A wire of length L. This is another question that is irrelevant to people taking the international A-level exam. Actually, it might be relevant to people taking Unit 1 at the AS level, okay? The international AS level. But anyway, let's move on. A wire of length L and diameter D is fixed at one end. A force F is applied to the wire, causing an extension E. A second wire made of the same material of length L and diameter D over 2 is fixed in the same way. A force 2F is applied to this wire. What is the extension of the second wire? Okay, so we have to use several equations. So the Young's modulus is given by sigma over the extension, right? And then we have that sigma is F over A. And then strain is given by delta X over X, okay? So if we plug, if we take these two equations and plug them in there, we will find that E is F over A times L over delta L, okay? Where I use delta L instead of delta X, but it's the same thing. So we have to solve for delta L because this is what we need. So delta L is F times L times 4 over E and then pi d squared, okay? And I use that A is pi d squared over 4, okay? Now the new delta L, and this is equal to E. I mean, this E over there. But now, I don't know why I'm using green. I'm going to switch back to black. So delta L prime is now 2F, because we applied twice the force, times 2L over the same Young's modulus, because it's the same material, times times pi, times d squared over 4. Okay, now it's correct. Okay, I'm sorry, because I messed up when we halve the diameter, we have to multiply by 4 in the numerator. So, okay, let's move on. Question 11. A student shown green light from a laser through a diffraction grating, producing a diffraction pattern on a screen. The student determined the angle of the third order maximum. Calculate the wavelength of the green light, and they give you the angle of third order maximum and the grating spacing. Okay, this is a question that does not appear in the international A-level exams. Okay, maybe in Unit 1. I haven't worked on that in a long time. So anyway, okay, the formula is the order of the maximum times the wavelength is equal to the spacing times sine theta. Okay, so we have to solve for lambda. So d sine theta over n, and d is 1.67 times 10 to the negative 6 times sine of 73.3 over 3. And this gives me 533.19 nanometers. Okay, question 12, wait, let me read it and then we'll see. Study of the photoelectric effect. Again, this is a question that appears in the international AS level exams, okay? So, study of the photoelectric effect leads to observations that cannot be explained by the wave theory of light. When light is shown on a charged zinc plate, electrons are released. When visible light is shown on the zinc plate, electrons are not released. State what is meant by threshold frequency. Okay, so there is a minimum frequency okay, F, such that HF is equal to the work function, okay? If F is larger than the minimum frequency, electrons are released. All right, part 2. Explain why the observation of a threshold frequency is not consistent with the wave theory of light. So if light was just a wave, okay? Eventually, electrons would absorb enough energy to escape, irrespective of the frequency of the light. Okay, I mean, there will be an accumulation of energy absorbed by the electron over time, and then eventually, after some time, if light was just a wave, the electrons will absorb enough energy and escape. Okay, so that's the idea at any frequency. Okay. Question B. The photoelectric effect can be explained using the idea of photons. State what is meant by the term photon. You can just write it's the quantum of electromagnetic energy. And you can also write H times F. I mean, it's the energy of that photon. Okay. Question 13. Aldebaran is a red giant star. Okay, I mean, it reads like a Lord of the Rings name or something like that. So, or maybe a Harry Potter name. So anyway, for a black body radiator of Aldebaran's surface temperature, the wavelength lambda max at which the intensity is maximum is 7.43 times 10 to the negative 7 meters. Determine the luminosity of Aldebaran. And they give you the radius. Okay, so we have the maximum, the wavelength at which maximum radiation is emitted, the maximum amount of radiation is emitted. So we can use Wien's law, okay? So lambda max times T is equal to 2.898 times 10 to the negative 3 meters Kelvin according to Wien's law. Therefore, T is 2.898 times 10 to the negative 3 over 7.43 times 10 to the negative 7. So you have meters Kelvin over meters. And by the way, for those of you who are watching my videos for the first time, whenever I use units, I always convert to the base units, which are meters, seconds, kilograms, amperes, what else? These are the usual suspects. Or what else? Kelvins for temperature. Okay. And I also put all my units to the right, so I can work with them, cancel them, etc. And I put all the numbers to the left. Okay. So the surface temperature is 3900.4 kelvins. So to find the luminosity, you can use the Stefan Boltzmann's law, which is sigma alpha, a t to the fourth, and a is the surface area. And for a sphere, this is sigma 4 pi r squared times t to the fourth. And if you plug in numbers, you find 4 pi, then 3.14 times 10 to the 10 squared for the radius, times the constant, which is 567 times 10 to the negative 8, times the temperature to the fourth, and this will give you 1.63 times 10 to the 29 watts. Okay, and that's the answer. And this is a valid problem that can appear in Unit 5 for those of you who are taking the international A levels. Okay. Moving on to question 14, which is only relevant to the UK A levels. Okay. It doesn't even appear in Unit 1 or Unit 2 of the International AS level physics, okay? So it's unique to England, I guess, and the United Kingdom in general. So, a student used two converging thin lenses in combination to form an image of an object. Show that the power of the combination of lenses was about 20 D. And I have to admit that I haven't seen optics in at least a decade, okay? So, but I took optics in college, so I know it. I mean, I know the theory, but I had to do a brief refresher. So, the power is given by 1 over F1 plus 1 over F2, okay? And the key word here is that these are converging converging lenses, therefore we take the power to be positive, okay? And we have to use meters, okay? So 1 over 0.1 plus 1 over 0.15, and this adds up to 16.7 D, which we will call 20 D for the purposes of the problem, okay? So part B, the object was about 4 centimeters in front of the combination of lenses. Calculate the image distance. Okay, let's find the combined focal length first. So since P is 16.7 D, this means that F is 1 over 16.7, which is 0.06 meters or 6 centimeters, okay? And then since 1 over V plus 1 over U, the distance of, what are we looking to find? The image distance, which is V, okay? And we know the object distance, which is U. So 1 over V plus 1 over U is 1 over the focal length, right? So 1 over V is 1 over 6 minus 1 over 4, so minus 1 over 12. So V is minus 12 centimeters. Okay, so negative means that the image is on the same side as the object. Okay. Part C, the object height was 1.4 centimeters. Calculate the image height. So the magnification is given by V over U, right? So we have minus 12 over 4, so minus 3. Okay, so the image height is equal to the magnification times the height, which is 1.4, so minus 4.2 centimeters. Okay, so the object is magnified. State two properties of the image. So this image is virtual because it's on the same side as the object, okay? Virtual and upright. Okay, and this was question 14 for our friends from the UK. Now question 15 is kind of a combination of material from Unit 4 and also Unit 2 from the international exam, but I would say it's mostly relevant to people from the UK again. So let's see it. A student, how do you pronounce that? Wound? No, wound is like when you injure someone. Wound, I guess. A piece of string around the head of an electric toothbrush. The student attached a small mass to the other end of the string as shown in photograph 1. The toothbrush was switched on and the head started to vibrate. The student rotated the toothbrush slowly to unwind the string. At a particular length, large vibrations were observed on the string. The string formed a loop as shown in photograph 2. Okay, so a loop, I guess they mean this. This is what they mean by a loop. Okay, I mean, you can see it. That kind of thing. Okay. A, explain how the vibrations of the toothbrush head caused the loop to form. So, so I guess you can think of this as a resonance. So you can answer like this. The toothbrush causes a string to vibrate at its natural natural frequency. Okay. The transfer of energy from the toothbrush to the string is maximum. Okay. So resonance occurs. Creating a standing wave with an antinode at the center. By the way, for those of you again who are watching for the first time, I think in I don't know, in British English, I guess you have to write it like this. I mean, center is written like that. But as I said in previous videos, I spend a huge part of my life in the US, so I write the same way as they write in the US. To me, this center reads more like the French centre, which means center as well. So anyway, this was a silly remark. Let's move on. A silly comment, not a remark. So part B. I dropped my pen for some reason. So the student continued to unwind the string and the loop disappeared. When the length of the unwound string was twice that shown in photograph 2, 2 loops were seen. 3 loops were seen when the unwound length was 3 times that shown in photograph 2, and so on. Determine the frequency of vibration of the toothbrush head when the unwound length of string with 4 loops is 0.69 meters, the mass of string is that, and they give you the mass per unit length. So what they mean, I guess, by 4 loops I'm going to use a clean page. They're talking about a situation that will look like this, I guess. So that's 2 loops, 3, 4. Okay. So we have 4 loops. Therefore, we immediately see that we have 2 wavelengths in the length of the string. Okay, so 2L is equal to the length of the string. So the wavelength is 0.69, because they give us that, right? Over 2, or 0.345 meters. Perfect. Okay, what else can we use? The weight of this string is m times g, which is 0.01, which is the mass, times 9.81, so 0.098 newtons. And this is equal to the tension on this string, right? Because the weight provides the tension. Okay, we know that the velocity of the wave is given for standing waves is equal to the square root of the tension over the mass per unit length mu, and they give us all that, right? So 0.098, and they give us the mass per unit length mu, so 9.1 times 10 to the negative 4 gives 10.38 meters per second. And we know that the velocity of a wave is equal to its wavelength times its frequency. So the frequency is v over lambda, or 10.38 over 0.345, which is 30.1 hertz, or 30 hertz. Okay. And this was question 15. Okay, let's move on. to question 16. This will have, in the international A levels, it would appear, a similar problem like this can appear in Unit 4, okay? So on the International Space Station, astronauts measure their mass once a month using a body mass measurement device, BMMD, okay? The BMMD is constructed from a large spring attached to the floor of the ISS with a platform and handles attached to the spring. The spring is compressed and the astronaut puts his body onto the platform and holds onto the handles as shown. Okay, that's a complicated instrument, okay. The spring is released and the astronaut and platform oscillate with simple harmonic motion. An astronaut used the BMMD, the frequency of oscillation was 0.34 Hertz. Determine the mass of the astronaut, and they give us the spring constant and the mass of the platform. Okay, so how do we think about this? The period of oscillation for a spring of any kind is 2 pi times the square root of mass, but here the mass is the mass we are looking to find, plus the mass of the platform, because they oscillate together, I guess, right? Over k. But they don't give us the period, they give us the frequency. So the frequency is 1 over f, right? But before we do that, yes, let's do this. So the frequency is 1 over, the period is 1 over the frequency, and this is equal to this over k. Let's take the square of both sides to get rid of the square root over k. Okay, let's use a clean page. So m plus m of the platform is equal to k over 4 pi squared f squared. So the mass we are looking to find is equal to k over 4 pi squared f squared minus the mass of the platform. And if we plug in numbers, we find that m is 350 over 4 pi squared, 0.34 squared, minus 5.7, which is 71 kilograms. To save time, sometimes I tell my students that pi squared is about 9.81. It's the same as g. Let me verify, because it's been a while since I said this. So p squared, it's actually 9.86. But yeah, you can take it as equal to 9.81 if you want to save those extra few seconds. So, okay, we found the mass of the astronaut. Cool. Part B, the distance between the upper and lower parts of the first oscillation is 0.29 meters. Calculate the magnitude of the maximum acceleration of the astronaut. Okay, so they pretty much give us twice the amplitude, right? Because they give us the distance between the upper and lower points. So that's twice the amplitude, right? Because in an oscillation, you have this situation. So they give you this, they give you the highest and lowest. So that's 2a. Okay, I hope this makes sense. Let me erase it. So 2a is 0.29 meters. Therefore, a is 0.145 meters. And then we know that the acceleration is omega squared times the amplitude. And this is equal to 4 pi squared times the frequency squared times a. And if we plug in the numbers, I'm feeling lazy, I'm going to just give you the final result. 0.66 meters per second squared, which is nothing, I guess. And part 2, calculate the speed of the astronaut 3.5 seconds after the start of the oscillations. Okay, this is a little bit involved, but you can use let me think. Oh, now I'm a little bit worried about something. Let me think. So calculate the speed of the astronaut 3.5 seconds after the start of the oscillation. So you can use the speed as omega a times sine omega t, okay? So omega is 2 pi times the frequency, which is 0.34, times the amplitude, which is 0.145. And then we have to multiply with the sine of 2 pi times the frequency, which is omega. This is omega, right? And then 3.5 seconds. How do I know it's a sine? Because at time 0, the speed is 0, right? I mean, you have to assume this from the way the problem is described, right? So, I mean, it's not at the maximum, right? You don't have any speed at time 0, okay? And don't forget to switch your calculators to radians, because we're using 2 pi there, the sine of 2 pi times some stuff there. So if you multiply all these together, you get 0.29, not seconds, meters per second. Okay, and by the way, the equations can be found in the back of the paper, as usual. Okay, so let's see. Are they here? No. Here. No. Here. Here. Yes. Okay, so that's the velocity. That's the acceleration. Sorry, the displacement and the acceleration. So let's go back. All right, this was question 17. It's a problem that can also appear in the international A-level physics exams, specifically unit 5. Let's go see it. A hot air balloon consists of a fabric envelope, heaters, and a basket as shown. Okay. When the balloon is set up, the envelope is partly filled with air at 20 degrees Celsius. The air is then heated to 120 degrees Celsius and expands to fill the envelope and becomes less dense. The air pressure inside the envelope is always equal to the air pressure outside the envelope because the envelope is open at the bottom. The balloon takes off when the upthrust is more than the total weight of the balloon. The air in the envelope and the passengers deduce whether the balloon can take off. They give you the volume of air at 120 degrees Celsius. They give you the density of air at 20 degrees Celsius, the mass of the balloon, the mass of the passengers, and the upthrust. Okay, so what are we missing here? We are missing the initial volume of air. So we have to use that to find the weight of the air at 20 degrees, right? So first of all, let's start with that observation. So let's use the ideal gas law. Pressure times the initial volume is equal to the number of molecules times K times the initial temperature. And then P times the final volume. And we are specifically told that the pressure is the same, so that's why I use P in both scenarios. And then the number of molecules, I guess, is the same because the air balloon is open. Therefore, you approximately have the same number of molecules, right? So you have to assume it's the same as well. So N times K times the final temperature, okay? So if we divide these two, we get these nice cancellations. And we are left with VI equal to Ti over Tf times Vf, okay? And the initial temperature is 20 degrees Celsius, but don't forget to convert to Kelvin, okay? Whenever you work with thermodynamics, please use Kelvin. It's safer, okay? So 293 over 393 times 2800 yields 2087.5 cubic meters, okay? So the total weight is going to be equal to the mass of the passengers times G plus the mass of the balloon times g, excuse me, plus the density of air times g times the volume of air we just found, excuse me. So this is equal to 3,335.4 plus 3,727.8 plus 2474.1, and all this is Newton. Final result is 31,637.3 newtons, which is less than the upthrust, right? So it will lift. We'll have a takeoff. Right. State one assumption of the kinetic theory of gases. Point particles, okay? Point particles. And then there is also elastic collisions. No forces between the molecules, etc. Okay. They ask for one, so I gave you three. What else is there? I don't remember. So anyway, so part 2, derive an equation to show that for a gas at temperature T, the mean kinetic energy of the molecules is 3/2 kT. Okay, so for this one, we can use the ideal gas law in this form. P times V, the volume is 1/3 times the number of molecules times the mass times the mean squared velocity. And we can also use the most popular ideal gas law, and if we set this equal to each other, we get nkt equals to 1/3 nm and then the squared velocity, so n cancels, and if we multiply both sides with 1/2, we get 1/2 m times the squared velocity is equal to 3/2 kT. This is an easy problem, okay? So let's do part 3. Calculate the root mean squared speed of nitrogen molecules at a temperature of 120 degrees Celsius. And they give you the mass of nitrogen molecule, which is 28 atomic mass units. And one atomic mass unit is 1.66 times 10 to the negative 27 kilograms. Do I remember it by heart? I do. Do you have to remember it by heart? No, but if you do remember it by heart, you're gonna save those few seconds that it will take you to turn to the back of the paper and read this piece of information here, okay? So most teachers say that you shouldn't memorize. I say you should for certain things, okay? So let's go back. All right, so let's just use the equation we just derived. 1/2 times m times c squared equals to 3/2 kT. Okay, so if we take the square root of c squared, this is what we need to find. This is equal to the square root of 3 kT over m, which is equal to 3 times 1.38 times 10 to the negative 23 times the temperature. Again, please convert to kelvins, 393, and then 28 atomic mass units, which is 1.66 times 10 to the negative 27. And if you go through all this trouble, you will find 591.6 meters per second, which is a really high velocity. So moving on to question 18. This is a question that if it appears in an international exam, it will be at the AS level. I think unit 1 goes over the photoelectric effect. But it's irrelevant to units 4 and 5 from the international exam. So in 1864, William Huggins and William Miller used dark lines in the spectrum of the sun to identify elements in the sun's atmosphere. Explain how gases in the sun's atmosphere cause dark lines in the spectrum corresponding to different elements. So, first observation is that in gases, electrons occupy discrete energy levels, which look like this. I mean, they might look like this, okay? So this is E1, E2, E3, and E4, and maybe this is delta E1, and this is equal to HF1, and maybe you have this transition here. Actually, it's better to name it delta 1, 2, okay? Maybe this transition is delta 1, 4, and it's equal to HF4, and so on and so forth, okay? So the key here is that every element has its own unique energy differences. Okay, and by the way, I wrote H times F. So what I mean here is that if a photon has an energy which is exactly equal to H times F1 here, for example, it's going to get absorbed, and the electron that was previously at energy level E1 will jump to energy level E2. Okay, so this is what I'm going to write now. So when a photon's energy matches the energy difference between two levels, it gets absorbed, and an electron moves to a higher energy level. Okay, so the absorbed photons appear as dark lines in the spectrum. Okay. B. The diagram shows some energy levels of a hydrogen atom. Okay. The absorption spectrum for hydrogen includes a set of lines that all derive from transitions involving the n equals 2 level. One of these lines is known as the hydrogen alpha line. Deduce the transition involved in the formation of the hydrogen alpha line, and they give you the wavelength of hydrogen alpha line as 656.46 nanometers. All right, so the energy difference is going to be equal to H times C over lambda. Okay, and this is the frequency, right? We don't need this. Let's move on. And if we plug in numbers, we will find 3.03 times 10 to the negative 19 joules. Okay. And since this transition involves the 3.4 electron volts level, let's convert that to joules. So 3.4 electron volts is 5.44 times 10 to the negative 19 joules. All right, so I guess the difference between these two, the difference is equal to 2.41 times 10 to the negative 19 joules, which is 1.51 electron volts. So the transition was from level 3, was from n equals to 3. Okay. Now part C. In 1868, William Huggins analyzed light from the star Sirius A. The wavelength of the hydrogen alpha line for light from Sirius A was slightly different from the hydrogen alpha line absorbed from a source in laboratory. Huggins suggested that this difference could be explained using the Doppler effect and could be used to determine the speed and direction of the star's motion relative to the Earth. And we have to assess Huggins' suggestion. Okay, so Z is equal to V over C. I mean, this is a Doppler factor, okay? And this is equal to delta F over F. So when an object, okay, I mean, this is what we know. So when an object moves away, the frequency is shifted. Okay. By how much it is shifted depends on the speed of the object. So he was right. So he was correct. Okay. Right. Part 2. Sirius A has a component of velocity away from the Earth of 5.5 kilometers per second. The wavelength of the hydrogen alpha line observed from a source in the laboratory is 656.46 nanometers. Calculate the wavelength of the hydrogen alpha line as seen in the spectrum of Sirius A. So Z is V over C. So 5,500 meters per second over 3 times 10 to the 8 meters per second, which is 1.83 times 10 to the negative 5, right? So delta lambda over the lambda in the lab should be equal to this difference, to 1.83 times 10 to the negative 5, right? And this is a unitless quantity, by the way, because we are dividing velocity V with C, which is also a velocity, so units cancel, okay? So it's a dimensionless quantity. That's the proper way to put it. So delta lambda is 0.01 nanometers, okay? So lambda in Sirius, okay, this is how it's written, will be 656.47 nanometers. Why? Because we have a redshift in this case, okay? Because Sirius A moves away from the Earth, okay? So we know that this is a redshift. If it was moving towards Earth, we will have to subtract that, okay? All right. So part C is a question that can actually appear in Unit 5 of the international exam. All right. And I think this is the last question. Nuclear decay is described as being spontaneous and random. A, part 1. State what is meant by spontaneous and random. So spontaneous means that decay, so maybe decays is better. So decays do not depend on external factors. Okay, and random means we cannot predict when the next decay occurs. All right, part 2. Explain why the decay constant of an isotope can be determined even though nuclear decay is random. So lambda, the decay constant, so lambda, which is the decay constant, is the probability that actually the probability a nucleus decays. Okay, so a nucleus decays per unit time, and this can be determined. So it can be determined because the number of decays is large, proportional to Avogadro's number. This constant can be determined. Okay, so the idea is that you take multiple measurements involving literally 10 to the 23 nuclei, and you can easily determine the decay constant. Okay, part B. A radioactive source used in a school laboratory emits alpha and beta radiation. Describe how the percentage of the activity due to the beta radiation may be determined using a Geiger-Müller tube and rate meter. So we need to measure the background radiation. Okay. Then we need to measure the radiation from the source. Then we need another measurement using a piece of paper to absorb the alphas. Okay, so we need another measurement using a piece of paper which will yield the beta radiation rate. Okay, so the percentage of beta, let's call it the activity due to beta radiation, will be equal to the the percentage of beta radiation, okay, just the percentage will be equal to the activity due to beta radiation only minus the background over the activity of the source minus the background times 100. Okay, and this will give you how much, what the percentage of beta radiation is from that source. Okay, part C. Americium-241 is used in schools as a source of alpha radiation. A pure americium-241 source was bought 34 years ago by a school. Determine the percentage of the initial activity that could be used today for the americium, that will be expected, today for the americium-241 source. they give you the half-life of americium-241 is 432 years. Okay, so from the half-life we can find we can find tau. How is it called? The decay time. So what I'm saying is that T1 half is ln of 2 over lambda, which is equal to tau times ln of 2, which is, tau is, T1 half is tau ln of 2. So tau, the decay time, is, I confused myself. What did I do wrong here? Yes, okay. So tau is T1 half over ln of 2, or 631.9 years. Okay, so the initial activity, the activity now over the initial activity will be equal to e to the minus time over tau, or e to the minus 34 over 631.9, which will give you 94.8%. Okay. So, is there anything else I want to comment there? No. Okay, that's the answer. And part 2 of question 19C. The decay products of americium are unstable and undergo a series of further decays. The table shows the first 3 decays in this sequence. Okay, so you have americium going into neptunium-237 in 432 years. Then you have neptunium-237 going into protactinium-233 in 2,100,000 years, and protactinium going into uranium-233 in 27 days. As student states, protactinium-233 emits beta particles when it decays, so by now the americium-241 source bought 34 years ago will be emitting a significant amount of beta radiation. Discuss the student's statement. So according to our earlier calculation, 5.2% of nuclei will be neptunium-237, it's written like this, nuclei. Okay, but because the half-life is very long, it's 2.1 million years, then very few nuclei in our sample will be 233 uranium nuclei after 32 years. It's 32, right? 34, sorry. After 34 years. Hence, we will not have a lot of beta radiation. So the student is wrong. And this was the first paper 2 past paper I'm going through. Okay, so I needed something different, guys. Okay, I mean, if you keep doing the same thing over and over again, you get bored. So as I said, the plan is to keep enriching this channel with more material. Okay, for now the channel is kind of stuck at the A levels, but hopefully I will start working on other topics as well. Let me know what you think about these videos. Please like, subscribe, and so on. If you want to support my channel, I have a PayPal link. So yeah, See you in the next video, guys.